If you've ever trained a neural network, modeled financial markets, or run a physics simulation, you very likely asked your computer to do something seemingly impossible. Give me a random number, but make it follow a normal distribution. But how does your computer actually shape randomness into that familiar bell-shaped curve? Surprisingly, one way to do so involves a 6,000-year-old architectural concept from Mesopotamia. It's the logic used by libraries like NumPy to handle multiple important distributions, and I love it because it brilliantly leverages key concepts like inverse transform and rejection sampling. By combining these concepts with a bit of clever geometry, the Ziggurat method can effectively cheat hardware limits to produce random samples from our desired distribution almost instantly. So let's learn more about these concepts and some of the ways our computer can generate randomness from a desired distribution. When we look at a continuous distribution, like the normal, exponential, triangular, or uniform, the y-axis doesn't actually give us a probability, it gives us a probability density. We denote this as f sub x of x, where the subscript capital X represents our random variable, or that which is uncertain, and lowercase x is a specific possible outcome. And because density is effectively measured as probability per unit length, the probability of any exact point is actually 0. However, we can calculate the chance that x falls within a range, and we do so by computing the area under the curve. While we can calculate the area of any slice of our distribution, one we're particularly interested in is the cumulative distribution function. This gives us the total area to the left of a specific possible outcome, representing the probability that x takes on a value less than or equal to it. And as we compute our cumulative distribution for larger outcomes, we are effectively collecting all of the density behind us. And because of this, the cumulative distribution function always starts at 0 and slowly approaches 1, representing the total probability of the entire distribution. And this is effectively a universal rule in probability. Irrespective of the chosen distribution, the resulting cumulative distribution must gradually increase from 0 to 1. And it's this exact principle that leads us to perhaps the most intuitive way to generate randomness, inverse transform sampling. In practice, this is a simple two-step approach. First, we generate a random value u from a standard uniform distribution between 0 and 1. Think of this u as a randomly selected cumulative distribution probability along our y-axis. And, fortunately for us, most computers can do this easily. We then simply map that probability to an outcome x via the inverse of its cumulative distribution. And for a uniform distribution, the math is incredibly clean. Because the cumulative distribution function is a straight line, the mapping is just a simple linear equation, an analytical solution. And modern CPUs love linear equations, making this mapping operation nearly instantaneous. But does it actually work? Well, let's run this algorithm 1,000 times, and apologies ahead of time for all of the dots that you'll see racing across your screen. However, notice that the resulting histogram shows exactly what we'd expect, a near-perfect uniform distribution. The mapping works out incredibly well. But if this works so well, why not use it for everything? The answer lies in the computational burden. For the exponential distribution, the inverse of the cumulative distribution includes a natural logarithm. And logarithms are transcendental functions, meaning they can't be solved with basic arithmetic. A computer can solve these in a single step, it requires multiple involved calculations. And for the normal distribution, the problem is even worse. The cumulative distribution function doesn't even have a closed form solution. To invert it, the computer has to rely on slow iterative approximations. And if you're generating millions of samples for a simulation model, this computational burden adds up quickly. To sample faster, we need a shortcut. And that shortcut starts with us understanding rejection sampling. Let's try to understand rejection sampling via this triangular distribution before introducing the Ziggurat method. We'll use a simple three-step process that fundamentally differs from inverse transform sampling. First, we'll sample a candidate value, x sub I, from a simpler proposal distribution, g of x. In our case, let's use that uniform distribution we just mastered. Second, we can scale the distribution by constant m such that mg of x umbrellas our target triangular distribution everywhere. Then, for our candidate x sub I, we can generate a second uniform random number, a height between 0 and mg of x. And finally, third, we perform a check. If the height is below our probability distribution of interest, f of x, we keep the value, and if it is above, we disregard it. A simpler way to visualize this algorithm is that we are sampling the area under mg of x with uniform probability. However, we are only keeping the points that happen to fall underneath our curve. And notice that, because our triangular distribution is taller on the left, we have a much higher success rate there. And this naturally weights our samples, ensuring we collect more values from the higher probability regions of our distribution. And here I've generated 1,000 samples via this approach, and notice that the logic holds. We have successfully shaped our generated data, but at a heavy price. We only kept about half of our simulations, and this highlights the first of 3 challenges with simple rejection sampling: efficiency. We need a proposal distribution g of x that is easy to generate from, but also tightly fits f of x to avoid throwing away many samples. Second, even in rejection sampling, we still must perform a computationally expensive check. For distributions like the exponential or normal, the probability density function itself contains transcendental functions. And this means for every draw, even the ones we reject, the computer still has to perform a relatively slow calculation. And third, for most important distributions like the normal or exponential, their distribution tail stretches to infinity, beyond the scope of this plot. And so we need a proposal distribution that can handle this situation. And so to solve these challenges, we need to rethink rejection sampling. We need to design a ziggurat. The basic idea of the ziggurat method is to replace one wasteful proposal distribution with a new proposal shape, a stack of horizontal rectangles that wrap our triangular distribution as tightly as possible. This ziggurat pyramid mimics our distribution far more closely than a simple uniform distribution ever could. And here's the genius part. Every rectangle has not the same height, but the exact same area. Because rejection sampling involves picking points uniformly under our proposal distribution, and equal area means equal probability, we can implement a brilliant 2-step shortcut. First, we pick a layer. Since the areas are equal, each layer is equally likely to be chosen. And we can do this by simply looking at a few random bits and indexing them. For a 4-layer ziggurat, a 2-bit index would select our rectangle. Second, we uniformly sample within that layer. We pick a random horizontal position x and use a cheat for speed. We compare x to the edge of the layer above us. These edges are pre-calculated to touch the probability density function exactly. And because they are stored in a simple lookup table, the computer can check them nearly instantaneously. If x is to the left, we are guaranteed to be under the triangular distribution, so we can skip the y-axis sampling entirely and accept the value immediately. No transcendentals need to be involved here. Only if we land in the tiny sliver to the right do we need to perform the actual check, sampling a y value and paying the computational cost to see if we're truly under the curve. So what does this look like in practice? In our 1,000 sample case using only 4 layers, the improvement is immediate. We keep 780 samples, a massive jump from the 528 we saw earlier, and we only had to perform an expensive check around half the time. And we can of course add more layers and simply use some additional bits for indexing to reduce the number of computationally expensive checks. For example, going from 4 layers to 16 layers, we'd only expect that we'd have to perform our expensive check 16% of the time. And if we scale to 256 layers, which is common in practice, that number drops to closer to 2%. So that's the gist of the ziggurat. Layers of equal area rectangles and a fast path for the majority of our samples. But to make this work for most distributions, we have 2 final hurdles to clear: the problem of infinite tails and the problem of symmetry. Let's first look at the exponential distribution whose tail extends to infinity. In our 4-layer case, we make the base layer special. It consists of 2 parts with a combined area equal to our other rectangles, a finite rectangle A1 and an infinite tail A2. Crucially, we define these 2 parts so they lie entirely within our exponential distribution, and this means that if we land in the base layer, we are guaranteed a valid sample. There is no rejection here, we just need to figure out where within it we land. And to do that, we first generate a uniform random value W between 0 and our total area, A1 plus A2. And you can think of W as the cumulative area we've traveled from the left edge of this layer. Therefore, if W is less than A1, we know that we're in the rectangle. And since area equals width times height, we can find our x-coordinate by simply dividing W by the rectangle's height, y naught. But what if we find ourselves in the tail of this layer? Since this part stretches to infinity, we can't use a simple rectangle, and so instead we use a very clever shortcut. We saw the probability distribution for an exponential earlier. It is just our luck that a shifted exponential distribution, one that only starts at the boundary r, perfectly encapsulates this tail. If we look at its probability distribution and move the terms around, we can see that this proposal distribution is simply larger than f of x by a factor of e to the lambda r. And so if we set our scaling constant m to e to the minus lambda r, these two curves match exactly. And because our proposal shape fits our target perfectly, the rejection probability drops to 0. And we can just use inverse transform sampling from earlier, but for a shifted exponential distribution to deal with this scenario. And here's the best part. This tail hacking isn't just for the exponential distribution. Because so many tails and statistics decay in a similar way, we can use the same shifted exponential trick to handle other important distributions too. Now while this might seem quite involved, remember that in a 256 layer ziggurat, we'd only expect to deal with this base layer case around 4 every 1,000 simulations. Now you might have noticed that our examples so far only go in one direction. They start high and slope downward. These are monotonically decreasing distributions where a one-way staircase of rectangles fits perfectly. So what do we do for a bell-shaped distribution like the normal? The trick is to simplify the problem. Instead of trying to wrap the whole bell at once, we build our ziggurat but only for the right-hand side, where the curve is once again downward sloping. And by only focusing on this decreasing half, we can use the exact same logic we've already perfected. And this is where we can use one final hardware cheat, the sign or flip bit. Once the algorithm has kept a point on the right, it looks at one final random bit as a coin flip. Either I leave my random value alone or flip the value, keeping it the same absolute distance from the mean but moving to its left. This allows a single one-sided ziggurat to cover the entire infinite range of the normal distribution. It turns a complex two-sided probability problem into a simple geometry problem on one side and a single bit flip on the other. Hopefully you've been able to learn through this video some ways that you can shape raw randomness into a bell-shaped curve. And definitely let me know in the comments if you want to explore other methods like Box-Mueller in a future video. Thanks as always for your support, and I'll see you soon.